In this lecture, we're looking at the subject of realizations. That's the topic. So this is part of our unit that we're looking at here. We've looked at dynamic models in general and state space models in particular. Realizations. So there are different ways of getting realizations for a system. So let's take a look. So part of this is, again, obtaining a model. Impulse response is one method. Difference or differential equations we've talked about a little bit already. So let's take a look at this impulse response method. So here we're going to start in the discrete time, and we're going to work with it that way. Now, if you have a linear time invariant system and you apply a delta function to the system, you'll get an output. Okay? So the delta function is the Kronecker delta function. Usually there are two different kinds of delta functions we work with. There's the Kronecker delta and there's the Dirac delta. The Kronecker delta is a discrete time signal that is 1 at time 0 and 0s everywhere else. Okay, so that's what we're talking about here. So we're going to apply the delta function to our system and see what comes out. So in general, for a linear time invariant system, we will have an impulse response that looks like this. If you apply an impulse to the system, you will get a weighted sum of lambdas. So in this case, I have lambda 1 to lambda n. And at the kth instance, we will get, so we'll get lambdas to the k. Okay, so this is the impulse response that we will get for a linear time invariant system. This is a single input, single output system. We could consider also a multi-input, multi-output system where the alphas are matrices, and they would be constant matrices. So we could do it either way. So it's simpler, first of all, just to consider the scalar case. So in general, the lambdas may be complex, and if the lambdas are complex, then the alphas will also be complex. Also, because if our system is real, if you have a complex lambda, you will also get its conjugate. So another one of the lambdas is going to be the conjugate. And likewise, the conjugate alpha will go with it. Okay, so in order for it to be real, you have to have both the thing and its conjugate. So this is the impulse response that you'll get for a linear time invariant system. It's of this form. I don't know what the lambdas are necessarily at this point, but this is the form that we will always get. Excuse me, not always. In the case that we have a system with simple poles. Simple poles, that is, not repeated poles. We can actually put one of these guys into a block diagram form that looks like this. Okay, we have a unit delay. So delta comes in, and it gets added to something. So if we assume 0 initial condition, that is, if the output of this is initially 0, the initial condition is on the memory element. A unit delay is a memory element. And so initial condition means this is 0. So at time 0, we have the delta function coming in. This is 0. So the delta function is 1 at time 0. So it comes here, goes through alpha, and it also goes into our unit delay. Okay, so at time k equals 0, this will be 1, which will make this alpha. So notice that when k is equal to 0, I'll get alpha times lambda to the 0, which is 1. So alpha. The next time through, the next time through the loop. So remember, in discrete time, we can think of it like a computer algorithm where you have a loop. And each time you go through the loop is the next k. So this is now 1. It gets multiplied by lambda. It gets added to this signal. This signal now is 0 for all time from time k greater than or equal to 1. And so now we just have what's going on in this loop part that controls everything. And so lambda times 1. And so the output now is alpha times lambda, which is what we would expect when k is equal to 1. Right? So this is now lambda. The next time through the loop, this is lambda. It gets multiplied by lambda, and it becomes lambda squared. So at k equal 2, we get lambda squared times alpha, and so forth. And so this is lambda squared. The next time through, this will be lambda squared. And so that gets multiplied by lambda again. And so you can see every time it goes through the loop, it gets multiplied by another power of lambda. And so you can see how this comes out. So this is the single mode case, or single pole case, where instead of having a sum of alphas and lambdas, we have just a single alpha and lambda. And this is what it looks like in a block diagram form. If we look at it in terms of now a sum of alphas and lambdas, this is what we could draw it to look like. That is, I have these loops, and I'll have n of these loops. Same delta function affects each of the loops, and each of the outputs goes and gets added to form the overall output of the system. So this is the so notice that when I apply delta to this signal is going to be alpha and lambda 1 to the k, and so on, all the way down to the nth value. This signal will be alpha n lambda n to the power k. And so we see that we can construct the general impulse response this way. Again, we can assume these are scalars, but this can also work. We can also do the same kind of thing with multi-input, multi-output system, where each of these alphas are matrices, and instead of having lambda, well, we would still have lambdas to the power k. So we could do it that way. And notice this delta is just still a single delta, and it gets multiplied by this matrix. Okay, so we could still consider it the in the multi-input, multi-output case. Now, how would we get a state model from this? In general, in defining a state model, we would define the output of each memory device as a state. So a memory device in general for a linear time invariant system will generally either be a delay or an integrator. So it'll be a delay in discrete time, it'll be an integrator in continuous time. We would then write equations for the input of each memory device in terms of only the input and the other states. Then we would put everything into a matrix equation. So in this simple situation, we would define the output of each memory device as a state. So here I have x1 to xn. So notice that if this is xn, if this is x1 at time k, then this signal on the other side is x1 at the next time. Okay, that is, this signal, after it gets delayed, becomes this signal. Okay, and so we actually, even though it looks non-causal because we're actually looking ahead, the way the loop is defined, we actually know what the next value of x1 will be. We know exactly what it will be because it's based on how this loop works. Okay, so, and basically I have the same thing for each of these states, and so I can write down the state equation associated with each of these states. x1 of k plus 1 is equal to, so that's the signal, it's equal to the input plus lambda 1 times the state. Now, so in general, in finding a state model, instead of now having a delta function, we're going to apply just a general input u of k. So instead of having zeros after the first, at time k0, we will have some other values. So I can write this, and I basically am going to write the same kind of equation for each of these loops. So here we are. x1 of k plus 1 is equal to u of k plus lambda 1 x1 of k, all the way down to xn of k plus 1 is equal to u of k plus lambda n xn. And so we have the state equations. We can also write the output equation. Y of k is equal to alpha 1 Oh, okay. Yeah, so let's look at the output equation. In terms of the state variable, y of k is equal to alpha 1 times lambda 1 times x1. Okay, so there, a lambda comes out in the middle of this. Notice, however, that the input u goes straight through. Okay, it goes straight through. And so we would have, this is our output equation, alpha 1 lambda 1 x1 all the way down to alpha n lambda n xn, and then we have the sum of the alphas times u. So this is the simple case, and now we can put this into a matrix equation. So here it is in the matrix equation. Notice that each of these equations, x1 only depends upon x1, doesn't depend upon x2, x3, xn, and so forth. Xn only depends upon itself and the input, not upon the other states either. So that would give us a diagonal matrix, and notice that u appears in every one of these equations, and so this is the form we get. So we get x's, all of the x's at the next time is equal to a matrix times all of the x's at time k plus this plus 1s times u in all of these cases. Similarly, we can write y out this way, and we now have a state model for the system with the impulse response that we showed. And it will be of this form in general. So what happens now if we have repeated modes or repeated poles? Well, generally, if you look at a form like this, alpha k lambda to the k. So notice this is multiplied by k here. And so basically you can go through and show that a block diagram that looks like this, with delta here applied, will give us this response. So the reason I've drawn a block diagram here is so that we can identify a state variable. So notice this is going to be a state variable because it's the output of a unit delay, and this is going to be a state variable because it's the output of the unit delay. So notice in this case, y is a function of this state variable, but not a function of this, directly a state of this state variable. Okay? So, if I string together L of these loops, this is what I get. And notice that I get a Jordan form. So, repeated eigenvalues is associated with a defective A matrix. Okay, a matrix that gives a Jordan form, not a diagonal form. So notice here I have ones appearing here, the way this is written, alpha lambdas, so forth. And the output y is going to be alpha times some some function of k times lambda to the k. So because if you recall over in this case, notice that I don't have identical loops. These two loops are not identical. And so that gave me a nice simple form. In the case when you use all identical loops, you'll get something instead of k, you'll get some function of k coming out. So this then is the impulse response. We've gone through and shown how to obtain a state model from the impulse response of a system. And again, you apply a delta function at time 0 and you see how the response is, and you match the response, and then you can get all of the states. Once you have the states, you can write the state equations. Once you have the state equations, you can put them into the matrix form.